some of the history of CAMs. We started running these in real time, NSSL in 2006, and then EMC jumped in 2007. And so have a decade of use of CAMs in real time, basically, to help with convective outlooks and forecasts. These are those early ones, obviously, NAM initial conditions and boundary conditions, no convective parameterization. They're cold start, no radar data assimilation. It's interesting because I don't think I say anywhere else that obviously I referenced the NAM CONUS NEST, which is convection line model. It's now at 3 kilometers, and they recently implemented with radar data assimilation the way the HER does it. I will actually come back on that a little bit. So some of the early forecasts, March 28, 2007. So this is some of the early indications of the utility. Wide longitudinal tornado outbreak on that day. But it's pretty interesting. The circles there, it's kind of how they used to indicate updraft helicity, highlighting within 25 miles of the point where UH exceeded a threshold. But I think the interesting thing of this is you can really see in these forecasts, even these early forecasts way back 10 years ago, the discrete nature of the storms. Now, they're a little too far east relative to where they happen. The observations are here. There's probably not enough storms in the ARW version. But again, it's not that you get the details exactly right in these models. You don't expect it to put it in the right county necessarily in a 24-hour forecast. It's just what's the mode, the general nature of the storms, and that type of information you're trying to get out of it. And then that's a couple hours later. But, pretty useful information in terms of mode. Perhaps you thought the storms were going to be discrete anyway because the shear vector was perpendicular to the axis of initiation. But nevertheless, it's just confirming, gives you more confidence in the forecast that that's the mode you're going to see. Here's a derecho of 2007 in August. You see the swath of wind reports across northern Illinois into southern lower Michigan. And again, you can really see the evolution in the NMM forecast. Clearly, there's a strong circulation, and within the model evolution of that MCS, and you can see sort of the bowing nature of the reflectivity signature. It's a little smaller scale in the ARW. In here, there's actually a sort of a secondary one, which, it's not exactly right, obviously, to what happened in terms of radar reflectivity. But, again, it's information to forecast, or maybe I should be thinking about the wind threat with this MCS. Okay, so some of those old examples showed how they kind of put a ring or a circle around, sort of top of the hour storm attribute information like UH, but that's not necessarily ideal. We'd like to have a little bit more information. Obviously, storms are evolving at much faster timescales than every hour. So how do you get that type of information? Can we pump out model grids every 5 or 10 minutes? I mean, in theory, it's possible, but when we're talking about operational systems and sending those types of grids, it's just not practical. And you'd think that capacity would increase with time as technology evolves, but it always lags behind the technology we're able to do. The capabilities that we have to run these models, the bandwidth and display capabilities always seem to lag behind. So I think a pretty good way to do it is what we term the hourly maximum field. So we basically keep a history of every model time step of certain variables we want to keep. It could be 2-meter temperature and dew point if you wanted max temperature or something, but that doesn't evolve as rapidly as things like the storm evolution. So we can track like UH every model time step within the model itself and then output what we call the hourly max field of that. And so that's pretty useful. You guys have likely seen those types of fields. So it's not necessarily new anymore as it's becoming more and more common, but it is a very useful way of sort of summarizing information without overwhelming the distribution system of this. So the main fields, again, are storm attributes. So reflectivity, we don't necessarily look at the reflectivity. I'll show you some examples. it gets streaky and long, and it's not how we're used to looking at radar observationally, so we don't necessarily use that. It's good for calculating probabilities and stuff. Updraft Helicity, it gives you a nice swath of rotation, so that's useful. Updraft speed, that historically had been calculated below 400 millibars. I'll show the next slide. We're trying to get implemented to look above 400 millibars. I'll show you why on the next slide. Downdraft speed, really, we've investigated it. We haven't really found a lot of utility in it. I think it's that the processes that drive really strong downdrafts occur at smaller scales, or the model physics just don't represent the downdrafts very well. And so you don't ever really see, especially we've looked at 4 kilometer grid spacing, very strong downdrafts, not nearly as strong as the updrafts. So I think that's, as we go to higher resolution, that will probably become more useful. But at this stage, the downdraft speed output doesn't seem to be very useful. 10 meter wind speed also seems to be a pretty strong underestimate of general wind potential. But if you consider lower thresholds, it does do okay. And then there's a vertically integrated grapple, which is supposed to be a proxy for hail. That field also is highly correlated with a lot of the other fields like updraft speed. We don't generally find a lot of additional utility from that type of field. Okay, so I've referenced the updraft speed. We generally did a search from the ground up to 400 millibars. That's what's in the models currently. But work done by Nathan Wendt at Sims here at SPC. This is just one run, but what we found is if you plot the vertical distribution of updraft speed, it actually peaks well above 400 millibars. And so when you extract it just below 400 millibars, you're really not getting the peak vertical velocity. So we thought this was pretty interesting. And we talked to Jack Kane, who sort of set the 400 millibar threshold back in the day. And he didn't really have a very good reason why. It was just, and that's what happens a lot of time in research. You just pick something and go with it and kind of forget why or how. And if you'd really investigated, it's actually better. So you get a little better statistical skill if you grab actually the maximum in terms of being related to hail potential, that type of thing. So we're going to actually look at that aspect some in this spring in the HWT. These are just some examples of the February 5th, 2008 tornadic outbreak, just to show some of the hourly max and what they look like. So you can see sort of the path of the storms. It's, not surprising what it looks like there. I think what's more useful is Updraft Helicity hourly tracks. So, rather than just a speckle at the top of the hour, you're getting sort of the path of the supercell over the past hour. And then, especially when you do multi-hour accumulation, I think that's where the forecasters really see the utility in it, especially at SPC when they're doing, a 24 or 20-hour outlook. They want quick summary information. I want to know the paths of the supercells during my valid outlook period. And so when you do these multi-hour outlooks, again, compared to the tornado paths on the right, certainly not perfect, not even close, but there's a lot of utility in that. Nevertheless, you get an axis of where rotating storms are going to be in tornado potential. The super derecho case, this one's pretty interesting when you see the simulations. This is sort of the end of it, early on the 8th, May 8th of 2009. A lot of QLCS tornadoes in there. But just a 10-hour forecast of these convection line models. They're NMM on the left and ARW on the right. If you look at it's pretty remarkable. Certainly something very favorable within the environment, forcing and instability and all that, pretty darn good forecast simulating this very intense Boeing convective system there. So obviously you'd want to look at, say, a 10-meter hourly max wind, and they both the runs produce 55-plus knot winds, and that's, as I mentioned, the resolution is coarse enough that that's an underestimate. Observed winds were quite a bit stronger, but again, if you understand the biases and the sort of the systematic under forecast of the magnitude, that's a pretty strong signal that there's going to be some damaging winds with that system. Okay, so just a quick summary of deterministic cams. I'm not leaving myself much time for ensembles, so I won't say too much here other than we now get a plethora of cams, so forecasters are kind of overwhelmed, which leads into the next topic, which is ensembles. Typically, they've been cold start, no radar data assimilation. It's becoming more and more common now to get some type of radar data assimilation. I mentioned earlier the newest NAM nest at 3 kilometers uses the same method, the digital diabatic filter, where you convert reflectivity into some heating rate to try to account for some of the impacts. It's not a perfect method, but at least you're getting some impact of ongoing convection when you start up a model, so it doesn't take as long to spin up storms.